This video will teach you everything you need to know about equilibrium for AP Physics C. I'm going to go rather fast because this is a really minor topic and you can also pause the video at any time. All right, so there are really two types of equilibrium, or two kind of forms of equilibrium. One is if the object is completely static. That means it's absolutely motionless, like my pen, and remaining so. The other type is where it may be moving, but the motion's not changing. By far, the most important type of equilibrium in this class is static equilibrium, so we'll spend most of our time on that. And here's the definition for one object. It's remaining absolutely still. Remaining still. It's not just temporarily have a speed of 0, it's actually remaining still, not moving in any way. So not moving sideways and also not rotating in place. So in other words, the velocity equals 0, and that's velocity of the center of mass. Velocity equals 0, and there's no rotation. Omega equals 0. So think about what that would mean in terms of forces and torques. If the velocity is staying 0, there's no acceleration. This means the sum of the forces equals 0. That's from freshman year. That's pretty straightforward. But if this is true, if omega is remaining 0, you might just think, oh, the sum of the torques equals 0, and you're done. That's not really true. The sum of the torques has to equal 0 around any axis. Any axis. And that's really the most important thing in these notes, is that concept that if something is remaining stationary and not rotating at all and not moving, then the torques have to add up to 0, not just around the center, not just around the center of mass, but around any axis on here. Because if they weren't, if you could pick a point and say the torques were uneven, like there's more torque counterclockwise here and clockwise there, it would start rotating around that axis. So for it to remain completely still, this has to be true. All right, I'm going to show you typical example concept questions you might be asked in this topic. Okay. For all of these, you start out with both of these quantities 0, and this is the question. All right, let's look at these 5 examples. In the first one, of course, it remains in static equilibrium. There are no forces drawn, so there's no way for the motion to change. Now let's look at this second one. And let's do our 2 checks. Do the forces add up to 0? Well, you have 3 newtons right and 3 newtons left. So yes, the forces add up to 0. Sum of the forces equals 0. But do the torques add up to 0? Especially around any axis. Well, we could dispense with that quickly by picking the center as an axis. And you'll see both of these are trying to make it spin clockwise. So no, the torques do not add up to 0. Torques do not equal 0, even around the simplest axis, so no. Okay, now let's look at this one. Clearly this is not in static equilibrium. The forces do not equal 0. So for this one, the F's do not equal 0, so the answer is no. Okay, now let's look at this one. 6 newtons right, 3 newtons left, 3 newtons left. Okay, so we have 6 right and 6 left cancels out. So sum of the forces equals 0. That's a good start. And next, let's look at the sum of the torques. All right, if we pick the center, you can quickly see the torques add up to 0. But if you pick any other axis, you'll find that the torques add up to 0 as well. For example, if you pick this axis, the 3 newton torque here is 0 because it's right on the axis. The 6 newton torque here is balanced out by the 3 newton torque that is twice as far away. And you can show quickly that that's true for any point you pick. So here the torques add up to 0 on any axis, so yes. And then finally, let's look at this one. The sum of the forces is 0. 6 right, 6 left. But let's look at the torques. And again, let's pick the easiest axis first, right at the center. There's more counterclockwise torque than clockwise torque, so sum of the torques does not equal 0, so no. All right, now let's look at an example problem. This is a typical example problem you'd have on an AP test or in the book. Okay, you've got a uniform slab and there's a person standing on it. The slab is 10 meters long and the person is 8 meters from the left. Mass for the person, mass for the slab. The slab is on 2 supports, and the question is, how much force is each support providing upward, F1 and F2? If all you had was F equals ma, Newton's second law, you could not solve this problem. If you drew a force diagram, in fact, let's draw the force diagram. Sum of the forces equals ma equals 0, because it's in static equilibrium, not moving. Remember, when you draw a force diagram, you only have to draw a dot. You don't have to actually draw the picture. So let's put our upward forces, F1, F2. Downward forces, 300. Gravity from here. And then this person is pushing down with a normal force, We'll write Fn, just to remind you, Fn of 500. So look what's happening here. Two unknowns. Ups equals downs for this thing to remain stationary or static. So F1 plus F2 equals 800. And if this is all you knew, this would be from, say, freshman year or earlier in this class, you'd be stuck. So you have to use this in static equilibrium and look at the torques. And for that, we need to use the extended diagram. In fact, we can just draw on the diagram we have here. F1 up, F2 up. This whole thing is 10 meters long. Okay? This provides a force, there's a gravity force of, in fact, we can just use these four forces and account for them on our diagram. We've got F1 and F2 already. Now let's figure out this 300 force of gravity pulling down. Where should I draw that on this diagram? Where is it going to apply a torque? Well, it's pulling on every part of this uniformly, so we can treat it as if it's all acting at the exact center. 300 newtons. All right, and then finally, this person's feet are pushing down with a force right here of 500 newtons. All right, that's that normal force. So we have two forces down, two forces up. We've accounted for them all. And now we're going to use it's in static equilibrium, which means there's no rotation, which means the sum of the torques equals 0 around any axis. So you've done torque problems. The most natural thing to do here would be to pick the center as your axis and then figure out the torques and make them all add up to 0. For example, you'd have F1 this way, that'd be a positive torque because it's counterclockwise. F1 times 5, 300 times 0, 500 times, what's this, 3? Yeah, a distance of 3, 500 times, that'd be a positive torque, and then this negative torque would be F2 times 5 that way. Okay? You could do that, and you'd get a long equation, and it would have F1 and F2 in it, and you could solve it, because then you have two equations and two unknowns. But notice I'm not doing any of that. Because if something's in static equilibrium, it means the torques add up to 0 around any axis. So let's pick the best axis. Let's pick the axis that makes this problem go by quickly. And if you do a few of these, you start to do that without any hesitation. If I pick an axis anywhere in here, both F1 and F2 are going to create torque. So I want to pick an axis so that it eliminates one of these letters, because that force will create no torque. So I'll pick an axis here. So I'll write chosen axis, choose axis. Here, that's where I choose my axis, because that creates an R, a distance of 0 to where F1 is, so that eliminates this torque. F1 provides no torque here. All right, so let's write this. Now I could write sum of the torques equals 0, but I'm going to use that kind of common sense thing that the counterclockwise torques equal the clockwise torques, right? If it's not moving, the counterclockwise equals the clockwise torques. So let's go through and do that. We want what do I have? Counterclockwise, clockwise, clockwise, counterclockwise. That's the only one that's providing a counterclockwise torque. So that's a distance of 10 from the axis times F2. Okay, here's my chosen axis, 10 meters times F2. All right, now let's look at clockwise torques. Distance of 5 times a force of 300. 5 times 300 plus distance of 8 times the force of 500. 8 times 500. Okay, and if I go through and do the math for that, I get that F2 equals, and you should of course always be pausing the videos and trying to do these on your own before I do them. I get F2 equals 550 without having to solve two equations and two unknowns. And of course I could go back and plug it in here and get F1 very simply. All right, and then the final thing I want to show you is a much less important case of non-static equilibrium. That's when something is moving, but the motion is not changing. So if we're talking about translational equilibrium, that's what you had in 9th grade. That's where the velocity is constant. So A equals 0, so sum of the forces equals 0. That's Newton's first law. We did that in 9th grade. That's translational equilibrium. You're talking about the center of mass moving, but straight and in a steady speed, because the sum of the forces is 0. All right, and then finally, if we have rotational equilibrium that's not static, rotational equilibrium, so spinning, but not changing its spin. So this would be where, and you should be guessing what comes next. Omega equals 0, or I'm sorry, omega is not equal 0, but it's constant. So that would mean alpha would equal 0. There's no change in omega. Okay? And you would say, therefore, the torques have to equal 0. Because, remember Newton's second law for torque? Sum of the torques equals I alpha. Just like Newton's second law for translational motion. If alpha is 0, then the sum of the torques has to equal 0. But, since this thing is spinning, since whatever it is we're talking about is spinning, it already has an axis. By definition, once it starts spinning, it has to spin around something, around a line which is the axis. So this it's not going to be the sum of the torques equals 0 around any axis. It's going to be the sum of the torques equals 0 only around the axis of rotation. This is unlike static equilibrium where the torques equal 0 for around any axis. Here, since it's already spinning, you only calculate that the torques equal 0 around that axis of the spinning.